Hi everyone, my name is Nadir. I'm a PhD student at UT Austin, and today I'll be presenting our work on programming and execution models for parallel bounded exhaustive testing. Automated software testing is essential for maintaining software quality, and automated test input generation greatly decreases the manual effort needed by developers. In this scenario, users write test generation programs that they then feed into a test input generator. This will then generate a number of test inputs which can be passed to a test suite. Our focus in this paper is on the test generation programs and the test input generator. One class of automated test input generation is bounded exhaustive testing, or BET for short. BET has been shown to be effective in finding bugs. And the motivation here is to generate all test inputs up to some user-specified bounds. For example, say we had a test that required a binary tree as input, and we wanted to test all inputs up to size 3. Well, first, we would generate one binary tree of size 1, then 2 binary trees of size 2, and then this is one of the binary trees of size 3. Now, there are two main questions that need to be answered when talking about bounded exhaustive testing. The first is, how do we write these test generation programs, or TGP for short? And there are three main styles here. The first is called the declarative style. Here, users write filters which encode properties that valid test inputs must satisfy. The second style is the imperative style. In this case, users write generators that describe how the test input will be generated. These two styles are considered to be restrictive, as users are typically locked into using either filters or generators. The hybrid style solves this issue by allowing users to combine filters and generators freely. It is therefore considered to be the most expressive of the three. The other important question is, how do we then execute these test generation programs? Existing work includes a hybrid approach, which is the most expressive. However, that work is sequential, meaning that it is slow and does not scale well, and it also uses a custom Java virtual machine, which is non-standard. There's also an existing declarative approach, which is the most restrictive, that uses parallelism, which makes it fast and makes it scale well. So what we're looking for is a system or a strategy that gives us high expressiveness with relatively low computational costs. And this is where Tempo comes in. Tempo is a programming and execution model for parallel execution of hybrid TGPs. The use of hybrid TGPs gives us high expressiveness, and the parallelism allows us to scale much better and gives us relatively low computational costs. This is an example of a hybrid test generation program. We have a generate BST function, which, given some size, will generate a binary search tree of that size. The first part of this function is the imperative generator part. Here, we first initialize the root node of the binary search tree. We then select the sizes of the left and right subtrees. We use this choice function to assign left size. For now, let us assume that choice will return a random value in the range specified by its arguments. So each time this function is called, choice will return a different value. We can then initialize the left and right subtrees, while also, and this init subtree function will also assign the keys to each node. We can then move on to the declarative filter part, which is made up of this rKeysOrdered function. This will check if the keys we just assigned are ordered properly for the binary search tree. Now, say we call this function with size equals 3, and say in the first execution, we get choice equals 2 for the left size. So we get this binary search tree where the left subtree is of size 2. Let us also assume that the keys were assigned properly, so we get this valid binary search tree. Other potential valid BSTs will include this one and this one. Now, it could happen that we will generate a binary search tree with an invalid ordering of keys, such as this one. So you can think of this problem as if though we're exploring a search space of candidate test inputs to extract the valid test inputs. And the key idea here is that these test inputs can be generated independently of one another using parallelism. And this is the high-level idea behind Tempo. These hybrid TGPs provide opportunities for parallelism. And we want to explore this search space by generating each instance of a test input using a separate thread. To accomplish this, Tempo provides an API for writing hybrid TGPs, 2 strategies for parallel exploration, and an OpenMP implementation for parallelism on CPUs, and a CUDA implementation for parallelism on NVIDIA GPUs. The Tempo API is rather simple and only includes 3 functions. The first is the explore function, which given some TGP, will explore the entire search space of this TGP and return all of the desired test inputs. The second is the choice function, which we've already seen. This will non-deterministically choose a value in the range specified by its arguments, so min, max. The third and final function is ignore if, which will stop the execution of the current thread if the condition is true. This will be used by the declarative filters to filter out certain test inputs that violate the properties. Now, moving on to the exploration strategies. TGPs specify a large search space of potentially valid test inputs. And essentially, these exploration strategies will explore calls to choice using one thread for each possible choice in the range. So max minus min plus 1 threads. And Tempo provides 2 strategies for parallel exploration, a fork-based strategy and a re-execution-based strategy. We'll even show another strategy which some TGPs will benefit from. This one will combine both fork and Reexe. So let's start with fork strategy. Fork strategy works by starting with a large number of threads. At every call to choice, we will split these threads evenly into different groups and assign each group a unique value in the range min max. So this is a code snippet from our binary search tree TGP. The first choice function assigns the left size of the subtree, and the second choice function assigns a value to a node or a key to a node. Say we start with 4 threads, and I will explain how we get this number later on. And with it, we then want to execute this TGP. We get to the first choice, which has 2 possible choices, 0 or 1. So we split this group of threads into 2, assigning 0 to the first group and 1 to the second. Then we continue execution, and eventually we reach the second choice. Once again, we have 2 choices. So we split each new group into 2 more groups. We end up with 4 groups with 1 thread each, with each group having a unique combination of choice values, 0, 0, 0, 1, 1, 0, and 1, 1. Now, one problem is, how do we select this initial number of threads? So 4 threads for the previous example. The solution is to add a thread estimation phase, which will run the TGP with a small, fixed number of threads to determine how many unique combinations of choice values exist. Moving on to Reexe strategy. Reexe strategy starts with a single thread. At a call to choice, it will record the number of choices needed and then stop execution. It will then re-execute the TGP with an increased number of threads. This time, when it gets to the same choice, it will have enough threads, and so it will assign each thread a unique value. So, given the same program, this time we're running with Reexe strategy. In the first execution, we start with 1 thread. We get the choice, so we stop execution and we execute again, this time with 2 threads, since choice had 2 possible values. This time, when we get to the same choice again, we can assign each thread a unique value. And then we get to the second choice, and here we have to stop execution again, and then re-execute, this time with 4 threads, because now we have 4 total combinations. And at the end of the execution, we will get to the same state as before, with 1 thread, with each thread having a unique combination of choices. Both fork and Reexe strategy will explore the same search space. However, fork strategy has to estimate the size of the search space first, and then start with that many threads. In some cases, we will have an imbalanced search space, and this will cause fork strategy to overestimate the number of threads needed, causing redundant threads, which will add substantial performance overhead. To see how this can happen, let's look at this program on the bottom right. Here we have 2 choices. However, the second choice will only be executed if the first choice returns 0. Fork strategy will estimate that the total number of threads needed is 4. And after exploring this program, we will reach this state. As you can see, the total number of unique combinations of choice values is only 3. So we have an extra redundant thread that does not contribute to exploration. We propose MixedStrategy, which combines both fork and Reexe strategy to solve this problem. It first uses Reexe to get the number of threads needed. So instead of the estimate, we know exactly how many threads are required. It then uses fork to explore the search space. You can find more details about MixedStrategy in our paper. Moving on to evaluation. We evaluated tempo by using 6 hybrid TGPs used in prior work. These are DAG, heap array, int RBT, which is a red black tree, SDLL, which is a sorted doubly linked list, and search tree. You can also find the specs of our machine on the next bullet. These plots show the size of the data structure being generated on the x-axis and the total execution or exploration time on the y-axis. We only include 2 plots due to space constraints, but you can find the rest of our plots in the paper. We noticed that initially, fork strategy outperforms Reexe strategy for smaller sizes. However, as we increase the size of the data structure being generated, Reexe strategy scales much better and outperforms fork strategy. The reason for this is due to the imbalanced search space that I mentioned earlier. Fork strategy will overestimate the number of threads needed and will run extra threads that will add substantial performance overhead without contributing to exploration. In summary, Reexe strategy is better than fork strategy for exploring our hybrid test generation programs. This table compares MixedStrategy to both fork and Reexe strategy for some of our test generation programs where MixedStrategy is effective. Compared to fork strategy, MixedStrategy is much faster and scales much better. This is due to fork strategy greatly overestimating the number of threads needed. Compared to Reexe strategy, we see that MixedStrategy is also faster. The reason for this is that MixedStrategy will only re-execute a smaller number of times when compared to Reexe strategy. We now compare tempo to other existing BET tools, UDITA and CoreAtG. UDITA is the original work on hybrid test generation programs. It uses a custom Java virtual machine to sequentially backtrack through all the calls to choice. CoreAtG is the GPU-based implementation of CoreAt, which generates test inputs from declarative specifications. We first note that tempo is faster than UDITA in all cases. This is expected as UDITA is sequential while tempo uses parallelism. When comparing to CoreAtG, our results vary by test subject. For heap array, tempo is faster. However, for int RBT, CoreAtG is faster. By examining the test generation program used in CoreAtG, we notice that the total number of candidate test inputs explored by CoreAtG is smaller than tempo. So CoreAtG has less work to do and will finish faster. However, this comes at a trade-off. By looking at the second table, which compares the lines of code in the test generation programs, we notice that the hybrid style, which is used in tempo and UDITA, is much more concise than the pure declarative style used in CoreAtG. So, in summary, tempo is on par with other existing BET tools and is faster in most cases. We also ran a case study where we tested C++ and CUDA compilers, namely NVCC, which is the NVIDIA CUDA compiler, GCC, and Clang. We wrote test generation programs that generated C++ and CUDA programs. Using a differential testing setup, we found 2 bugs in NVCC and 2 bugs in Clang. You can find additional details in our paper, such as formal details on the exploration strategies, some low-level implementation details, as well as details on how we scale beyond the hardware limits. You can also find more details on MixedStrategy, as well as some data for sequence-based test generation programs. We also include data for profiling tempo on the GPU, using metrics such as warp divergence and achieved occupancy, as well as more details on the case study and bugs found. Finally, there is a discussion on the test generation versus test execution time. In conclusion, tempo is the first work on parallelizing hybrid test generation programs. It offers 2 novel execution strategies, and we present an extensive evaluation on various data structures used in prior work. We show that the performance of tempo is on par with the more restrictive BET tools. Tempo is open source and is available at this link. And this work was partially supported by the NSF and partially supported by Google. Thank you.